So next we have our first keynote. Our speaker is somebody to get very excited about. He works from Mozilla Research, works on the compilers and language team for Rust. And the one thing that I'm most excited about for Felix's talk is that it really combines sort of something very unique about Rust. The ability to really have your head in the clouds and thinking in things like category theory and advanced type systems, but at the same time having your toes wrestle around inside the bits. So I think everybody here is going to enjoy what Felix Klock has to say. So welcome Felix to the stage.
Okay. Secretly type in my password. Okay. All right, I'm really happy to be starting this thing off. This is the first time I've given the first talk at a conference, which means I get to actually pay attention to all the other talks. It's the first time in my life I've been able to do that. I'm really looking forward to everyone else's talk. So this is this talk. All the slides are already online, so if people want to take a screenshot, a photo, so you can go to this link here and get ahead of me if you want, or follow the links that are in there. I recommend you do so now because this URL is not on any other slide. So this is the time to do that. So having said that, I'm now going to go forward. So this is a talk. I was invited to give a talk about a technology talk, and I took that as a challenge. And so an interesting thing about technology is that Arthur C. Clarke has this law, his third law, that any sufficiently advanced technology is indistinguishable from magic. And that's kind of an interesting thing that we'll talk about in a little bit. There's also this important second law, which is that the way to actually discover the limits of the possible is to push the boundaries until you hit the impossible. And that has lots of different interpretations. Here, we'll explore this by learning about what the limits are of the technology in Rust by actually trying things out and seeing where do we break things, where does the compiler stop accepting our program. There's also a first law, but it's not relevant to my talk. It's something about impossible statements and elderly people. There's a lot of interesting technology in Rust. There's lots of things I could have potentially talked about, the borrow checker, or our interesting trait system and how the static polymorphism of traits interacts with dynamic dispatch in its object system. There's destructors, which I'm kind of crazily obsessed about, the dynamic destructor semantics and drop and whatnot. And then there's match, which you wouldn't think is all that interesting, but there's some interesting details there. So all of those can look like magic, but subtyping is a really interesting thing. It's a little bit more like a magic show in that everyone already knows what subtyping is. If you already know what it is, then it's a lot easier to sort of get fooled and see interesting things happen that you didn't expect. So a little comment about magicians. So I heard this great statement from Penn Jillette. Who here has heard of Penn and Teller? Okay, great. So Penn Jillette's an interesting guy. He's the one who speaks between Penn and Teller. Teller's the one who's silent. Penn actually talks a lot. And so Penn has this quote. He talks about when he first started learning magic as a young child, or young adult, I should say. And he actually had a turning point where he came to hate magicians because he realized these people are up there on stage lying, and he was devoted to telling the truth all the time. And he thought, so I can't do this. I can't lie to my audience. And he attributes James Randi with giving him the idea of a turning point here, where he said, you don't have to lie. You can be honest the whole time and still be a magician. Or rather, you can lie as the entertainment, but still be honest and moral. But what Penn does is he tells the truth the whole time he's talking and lets the audience lie to themselves in their heads. I'm going to try to do the same thing. I'm going to try to be honest during this whole presentation, but I might make some mistakes. Hopefully I won't. But usually the trick is going to be getting you in your heads to to lie to yourselves. Since this is a magic show, I'm obliged to show you there's nothing up my sleeves. So let me take care of that right now. Oh, I knew that was going to happen. There's something behind my back, of course, but nothing up my sleeves. All right. Quick poll, just so I can understand what the audience is like. Raise your hand if you know what the playground is, if you know what playwrestlinglet.org. Okay, great. So how about if you know the difference between a slice and a vec of t? Raise your hand for that. Great. And finally, do you know what phantom data of t is? Raise your hand for that. Oh, wow. Okay, that's more than I expected. Great. Maybe this will be a boring talk. So let's ask ourselves, what is subtyping anyway? I claimed earlier that we all already know what it is. Well, the important thing about subtyping is that it's meant to be this thing where if you don't have subtyping, if your compiler insists that your expected type always matches the exact type that you're providing, the type of expression you're giving, if you require those things always match, the compiler will often reject programs that seem obviously well behaved. So there's intuition here that comes into play about the provided type somehow being compatible with the expected type. And so we can think of some examples in Rust where this seems to come up. If I have a mutable reference to a vector, but I want a slice, those seem like they might be compatible. Maybe I can just pass that in. Or I have a string, and this thing takes a string slice, a stir. Or I need to return an error, IO error. That's why I have an IO error in my hand, but my function itself returns result with a parse error. And the interesting thing is that in Rust, you oftentimes can just try out, just passing along, and find out if you get that kind of compatibility, if it turns out that this thing seems like a subtype of another. So this talk is going to be all about trying out things and seeing if they just happen to work. Whenever there's blue in my talk, it means there's a link to a playground session or some other page, but usually playground, so you can try it out yourself if you're following along on your phones or whatever. But since not everyone has their phones, we'll actually show you the example. So here we have something that might have been in the compiler at one time or some point in the future, where it's a phased compiler, so that phase 1, we get the abstract syntax tree, and we're going to produce mir as an intermediate result. And then phase 2, we're going to take the mir and produce output. And each of those phases has distinct errors. There's the possible phase 1 errors, possible phase 2 errors. The question is, if I compose these two things, can I do that and have an end-to-end error of some kind? It turns out that you can just run this code, it'll compile, and be just fine. This seems like it could be subtyping. Maybe phase 1 error and phase 2 error are subtypes of end-to-end error. We'll be looking a little bit more at this later, this particular example. And I mentioned before, vectors and slices. That also kind of looks like subtyping. We've got a vector, and we need to have a slice of t. So what happens then? So I have a specific program here where it's this dummy little rotate program that takes a slice of integers, 32-bit integers, and all it does is it saves the first one, then shifts all the other ones up, and then it stashes that first one at the very end. So really it's just rotating the whole slice by one element. And you can just try this out and see if this compiles. Like make a vector, try passing it in. Does this compile? And in fact, this doesn't compile. But it doesn't compile because of some incompatibility. It compiles that you often, if you program in Rust, you've probably had this experience of trying something out, and it turns out, oh, there's some small changes I need to make, right? I had to make the v mutable, and I have to actually grab a mutable reference to v by doing ampersand mut v. This bottom one is the version that works, but still we're seeing this phenomenon where I can take a mutable reference to a vector and pass it to a context that's expecting a slice, a mutable slice. So that's interesting. For all these other examples in the talk, though, you may have noticed it took me a little while to explain the rotate function and what it does, and that's going to be a bit of a waste of time when we're just trying to focus on subtyping. So like good scientists, we're going to try to reduce ourselves to a model to explore. So here I'm just going to try to always strip my examples to this minimalist form, where in this case I talk about I have something I want to provide to somebody else. So I have a mutable reference to a vector. That's what the provide function has, and I want to pass it to a context that's expecting something else. It's expecting a mutable reference to a slice of integers. And so I've got that up here. That's the kind of code that is really presenting this idea of these things being compatible. And it's also in pictorial form with taking a mutable reference to a vector and passing it into the expect function. And the overall idea is that if these things compile, they work. I'm not going to worry about it running. If you try to run this code, you'll get an error because there's that unimplemented macro in there. So of course you're going to get a runtime error. The whole point is just to see, does the compiler accept this code right now? That's the name of the game. So another example of a place where you might see some compatibility relationship is when you have a mutable reference to some type t, and you need a normal reference, an immutable reference to t. And so maybe there's some sort of compatibility relationship there. Again, we can just try it and see using the same kind of skeletal form, stripped down form I just showed, where we're providing a mutable reference to some slice of integers, and we're going to pass it to something expecting an immutable reference. Again, this compiles. And now we're going to go through and see some other examples involving methods. So methods in Rust, if you have the keyword self or the capital S self, either those kinds of self, then you're usually talking about some sort of method. And what I want to do is I want to talk about all the possible combinations of either taking something by value with just self itself, or taking something by reference, or taking something by mutable reference, and seeing the way you can combine these things. And we're going to be looking at methods on char arrays. But before we jump into that, I want to just review something for people who don't necessarily know about this particular programming pattern. If you have a built-in type like char, and you want to add methods to it, you can do that in Rust by making a trait. Here, I'm giving the example of a trait ASCII inker, and I'm trying to add this inker method to all chars. And so I'm just saying, this thing, all it does is increment self by 1 unit. So for example, it'll take the letter A and turn it to the letter B in ASCII, at least. And so the way it's implemented for char is this code here. It doesn't really matter the details of that. The important thing is this sort of works. You know, I have a little test here showing if I start with A, I call inker, I get out B. I'm just reviewing how method extension works in terms of using a trait to add new methods to a type. So having said that, I now want to show you a different trait where, again, the whole point is just to focus in on, can I pass one thing into another place that's expecting something else? So I've made this dummy trait receiver, and all I'm trying to do here is demonstrate 3 different kinds of methods. There's a method where you take self by reference, there's a method where you take self by mutable reference, and there's a method where you take self by value. You can see the 3 different kinds of selves there with the ampersand self, ampersand mute self, and the by value self with no ampersand at all. And then I've got the implementation of this method, or the implementation of this trait for a char array, where all it's going to do is print out which case we're in, and it's going to then print out, and then it's going to try to modify the second element of the array for the cases where we can do that. When we get something by mutable reference or when we get something by value, we can actually mutate the input. So here's a sanity check first, just to make sure we understand what this trait does, where I'm just going to show you. I create 3 different char arrays, and then I call the 3 different methods. So I create a char array A, that's just the array itself being passed around by value. There's no references involved. There's B, which is a reference to a char array. There's C, which is a mutable reference to a char array. And then I call A by val, B by ref, C by mute. These are the things that match up exactly to what the original type is and what the expected type is. There's no interesting compatibility issue here. It's just inputs match the outputs. And when we run this, you get exactly what you expect. It prints out, I called val, I called ref, I called mute. And then I obviously have these 3 arrays at the end. It may not be obvious why that's the case, but that's not really the important thing here. The important thing is just that these cases are compatible, and you may have noticed the very interesting layout that I chose for this code, where it's got this diagonal that's going across, and that's because there's not just 3 cases to consider, there's 9 cases to consider. I want to try every possible input, value, immutable reference, mutable reference, with every possible expected input, all 3 methods we could call. So that's a 3 by 3 grid, which looks like this. And the interesting thing here is that if we were to fill in all of the elements of this grid, it wouldn't compile. But if you remove one of the elements of the grid, the B by mute, where I've got that comment there that's commented out that element, that cell at the bottom there where you see there's a middle column and something's missing, this now compiles. The only case that's rejected by the compiler is B by mute. And that's kind of interesting, because this means, it seems like, you can go from an immutable reference, going from an immutable reference to a mutable one, that's disallowed. But for some reason, going from a value to a mutable reference is allowed, and perhaps even more strangely, going from a reference to a value is allowed, and so on. All those other cases are allowed. So you might ask yourself, wait, how is this actually happening here? What is going on? Are these things subtyping at all? What are we talking about? So to get, from the point of view of like a person who's experienced doing Java VM runtime hacking or hacking for other kinds of dynamic languages, you might say, look, the representation of these 2 types, a vec is represented by 3 words directly in line, like embedded in your stack frame, and the slice is represented by 2 words, and the layouts aren't even compatible with each other, like the len is at the wrong place. So how could these things possibly be subtypes of each other? If you're thinking about the runtime representations and how things work, That doesn't make any sense at all. You can't just pass in a slice wherever a vec is, or you can't just pass in a vec with 3 words into the spots that are expecting a 2-word slice. That doesn't make any sense at all. But I have to take a moment here and point out, I myself had that initial reaction, and then I started reading textbooks about subtyping to double check whether my thinking was right about this. And the textbooks in subtyping, they're like, oh, no, there's other semantics where you like talk about coercions between things where that can be considered subtyping, so so-called coercion-based semantics. Okay, so let's wonder for a second here, is this subtyping? And what I'm going to do is, I just spent a little while talking about those examples, and now I'm going to put them aside temporarily. We'll come back to them. To first explore this textbook notion of subtyping. So a classic example of subtyping in the textbooks is they'll talk about records. They'll talk about anonymous records, and they'll say, oh, if I've got 17 fields in my struct, and I want to pass it somewhere to a place that expects just 2 fields, but they have the right names and the right types, they should be compatible. A Rust analog to this would be if I had a tuple of 3 elements and pass it to a place that expects just the first 2. Does that work? And the answer is no, it doesn't. This does not compile. There's interesting questions as to why that might be a good idea to not allow this to compile. And another example of textbook subtyping, the more sort of fundamental one for the academics, is what happens when you have functions. So if we start off with an assumption that we're going to have some basic type like integers and reals, and we're talking about like in the mathematical sense here. I don't mean real like floating point numbers. I mean real like supporting, representing things like pi exactly, like being able to generate all the digits of pi to whatever precision you want, etc. So there's interesting questions then when you have that kind of subtyping, where you say, okay, well I have a function that's of type real arrow int, and I want one that takes real to real. Is that legal? Or how about a function that takes int to int? Can I pass that to a place that wants a function that goes from reals to reals? So let's talk about that last example first. If I have a function that takes integers to integers, and I want to pass it to some place that needs a function that takes reals into reals, is this going to work? And the answer is this won't work, because the integer to integer function, it assumes its input type is always integer. And so you're going to break things if you pass it to a client that wants a real-to-real function, because that client might pass it a real number. My function wasn't written to support that. So here I have an example where we have a twice function that applies its first argument twice to its some input, and there's a num divisors function that assumes that it's given an integer. It's going to give you the number of divisors for that integer. I give some example inputs and results for that function. And the point is that if you try to apply num divisors using the twice function, you get nonsense. You're going to try to eventually apply num divisors to 2.3, and that doesn't make sense. You can't talk about the number of divisors in a sensible way of a number like 2.3. It doesn't make sense. So the point here is just to show that definitely, no matter what, int arrow int is not a subtype of real arrow real. It does not work. Okay, but there was another example I gave. If I have a function from reals to ints, and I want one that takes reals to reals, does that work? So in this case, this actually works out. It's something where you can have a function that takes reals to ints and pass it to something that wants reals to reals. I gave an example here of passing a ceiling function, this modified ceiling function that into the twice function, and it all works out in terms of you plug the types together and there's no errors along the way. And this kind of makes sense. If we ignore what I was saying before about runtime representations and them having to be compatible, mathematically this seems like it should make sense. And the reason it makes sense is because the client is saying, I handle any real number. So if you give me something, as in I'll give a real number and I'm going to handle any real number back. So if I give a function that is guaranteed to turn reals into integers, that's fine. The client's able to handle integers. It said I can handle any real, in fact, that I get out from this function. So it's obviously fine to narrow that to just integers in terms of the function I hand to it. Okay. So how about this example? I have a function in my hands that takes reals to integers, and I want one that takes reals to reals. I just talked about this, didn't I? Right, that is exactly what I just talked about, but I wanted to show you what this looks like in Java. So in Java, you could encode this by having a class real, and then methods on it that return reals. And the point is, if you then have a subclass int that extends real, you can have methods that return int. Java compiler compiles this just fine. And actually, if I want to encode this more accurately, I would really talk about real fun that turns reals to reals, and int fun that turns reals to ints. But actually, the interesting thing here is that Sun didn't originally support this code. It only added it in 2004 with this thing called covariant return types. And that's the first occurrence I think we've heard the word covariant. We'll talk about that in a little bit. So to try to reason about these kinds of relationships, to be able to argue why int arrow int and real arrow real are not subtypes, but while those other examples are subtypes, type theorists often use these things called deduction rules, where they'll write a precondition and a postcondition with a line between them. So, for example, of one of these would be, hey, if A is true and B is true, then the statement A and B is also true. That's the kind of reasoning you can do using these rules. And so a rule for function values would be, if I can prove that y is a subtype of x, then I should also be able to prove that A arrow y is a subtype of A arrow x. And this is, the other way of stating this is that the arrow operator is covariant with respect to its return type. So the example here that we've been talking about is if int is a subtype of real, then real arrow int is a subtype of real arrow real. So again, it's just the reasoning. All the caller can do is get out an x from calling the function. So it's safe to narrow it and say, I'm going to definitely always give you a y, and the caller's fine with that. They can handle y's because they can handle x's, and y is a subtype of x. Okay, now we turn things on their head and say, okay, well, what about if I have a real arrow int, and I want a function that takes ints to ints? And this is known as contravariance. The idea here is the client is saying, I will only feed integers into the function. And if you give me something that can handle reals as well, that's gravy. Not all languages actually support this. That example I gave you before where I encoded the covariant return type in Java, if you try to encode this example, it won't work because Java has overloading on its input types. And so it doesn't work out the same way in terms of these things being subtyping. But having said that, this is what the type theorists would write down. They would say, look, in fact, if I could have these two distinct relationships, y is a subtype of x and b is a subtype of a, then a arrow y is a subtype of b arrow x. Covariant with respect to return type and contravariant with respect to argument type. And again, this is just me repeating myself. The idea is the caller can feed in a specific b and get out the more general x. And it's safe to be more liberal and provide a function that then can accept any a at all, generalizing the potential inputs and narrowing the potential outputs to y. And as a quick aside here that will come up later, what happens if you restrict the domain and range? If you want to have y arrow y and x arrow x, what should the top of the line be? What should the precondition be? Think about that for a little bit in the back of your head. So now we might ask the question, well, does Rust have these properties? Does Rust have this kind of variance property that I've been describing? Well, we could try plugging in those types I just showed at the very beginning, all those examples I gave of compatible types. So here I have a reference to a vector and a reference to an integer, and I showed how, on the left-hand side of this picture, how these things are compatible. But if I try to generalize that to this variance type stuff in terms of functions and actually make a function type that returns a vector and pass it to a thing that wants a function that returns an integer slice, it turns out this doesn't compile. The Rust compiler rejects this. So there's something funny going on here. The left-hand side compiles, but the right-hand side does not. Likewise, if I encode another one of my examples, that thing where I talked about a mutable reference to a slice and passing it to a context that expects an immutable reference to a slice, again, the higher order generalization where I've made these functions that return a mutable reference and it wants a function that returns an immutable reference, again, code does not compile. So, from these examples, it sounds like we might conclude that Rust does not have variance. It doesn't have covariant return types. It seems like. So, having gone in deep into this topic, I'm now going to do a magic thing and totally misdirect you and talk about something completely different to make you not think about what I've been talking about for a while. So here's a little story from my interactions with one of the servo developers. So Simon Sapin, who's actually here right now, you can talk to him more about this and see if he remembers this. He came to me and said, I have some code that doesn't compile. And I don't understand why it doesn't compile, but I worked on it on my own, so what I decided to do was reduce the code down to a minimal thing that I could understand. So I came up with this minimal example that used the standard library type cell. But I didn't even understand that. I still didn't understand why it didn't compile. So I decided, well, I don't understand the source code to cell, but I can look over it quickly. I'll make my own version of cell as well, and maybe that'll help me understand why this doesn't compile. So Simon made his own version of cell, and when he did that, the problem went away, and his code started compiling. So let's try this ourselves. Let's make the standard library cell ourselves. So here we have my cell, and it has some type T. It stores an instance of T within itself, just embedded directly within it. And what you can do, you can create a cell. All you need to do is call new and pass in one of these T's. You can get the value from the cell. This makes sense because T is copy, so it's safe to do get and just copy out the value within the cell itself and makes a new copy of it. And then the interesting thing is the set method. And what the set method does is it uses a little bit of unsafe code to say, let's grab a reference to that embedded value and then use the unsafe method pointer : write to write in the new value that's going to go in there. So this is some code that seems to behave the way that cell should. And a fundamental question right now is this sound? Is this version of this code sound? Is this use of unsafe sound? And the answer is that this is actually completely and totally broken. Please do not do this. Please do not go and take this code and use it in your own projects. It does not work. It is bad, bad, bad. There's many reasons for this. One reason is that there's secret information that the compiler makes use of that the standard library cell knows about, and this code does not, that can expose brokenness with respect to parallel execution and aliasing stuff. That's one reason. But even in the single-threaded case, this is still broken, and that's what we're going to be talking about right now. So there's another subtle reason that this is broken. So let's talk about this. Why is this broken? Here is some code. Now, don't panic. This is complicated code, and I don't expect you to understand it immediately, although I do have a link to it as usual, so you can go and follow that don't panic link to the code. We're going to step through it. But the important thing is I want to point out there's two printout statements. There's a printout statement where we print out the value of this thing, this cell, at the point in the execution where it's at the end of step 1, and then we also print out the value at the end. So we do that twice. And you may notice here that there's two interesting numbers that occur in this program. There's the number 10 at the very top where we define the static variable x, and there's the number 13 that occurs when we have this local variable val inside of step 1. When we run this code, it prints out 13 for the value at the time of step 1, and then on my machine, it printed out 28,672 for the value at the end. When you see this kind of thing, this is usually a sign that something terrible has happened. When you have random numbers just pop up. So you see garbage like this, that's usually a sign something is very wrong. But I want to explain how this is happening. So again, this is the same code, except I reduced it a little bit to fit on the slide. We're going to create a cell, this my cell thing. We're going to call step 1, and then so here, let me show you a picture. So here's a picture where we have the cell itself, and it starts off with a pointer to the static data area. It starts with a pointer to x. That's what we create at the initial step 1 call. We're creating a reference to, or the initial cell, let cell equal call is creating a cell with a reference to x. Then the next line, we're going to call step 1. So there's a new stack frame now below it on the stack, and it passes in a reference to the cell. So we took a reference to the cell, that's what RC1 is on this diagram, and there's a reference to the cell itself, as well as the value we've created on the stack frame, the value 13. Then we call step 2 with a reference to the value. So now we have another stack frame that points to the val, and we have another reference to the cell, RC2. Then we call set with rval, so we've moved the pointer so that cell now points to val on the stack frame. We pop the stack once, and we ask, hey, RC1, what do you hold? And it says, oh, I hold 13. That's the first line that we saw in the output. And then we pop the stack again, and we have a dangling pointer. So this is no good. This is the kind of bug that Rust is supposed to stop. We aren't supposed to have dangling pointers anymore. So either my cell is broken, or the Rust compiler is broken, or the Rust language is broken. You know where my belief is here. So the question here is that, okay, well wait, is cell also broken? And the easy way to test this is plug in cell into that same code again. If we plug in cell into the same code, the exact same code I just showed you, the compiler rejects it. The compiler tells you, no, we're not allowed to take the reference to val when you make that call to step 1. It doesn't live long enough. It has to live as long as some lifetime a, but the value borrowing doesn't live that long. So the compiler is smart enough to reject this when you use cell. And the question is, why is this happening? What is the difference between my cell and cell? I went to the source code and found out look, my cell says it has a value, and cell says it has an unsafe cell, and the unsafe cell says it has a value. What's the difference here? Of course, the difference is that there's this special unsafe cell the compiler knows about. But still, why are we accepting the my cell code and rejecting the cell code? And the answer, ta-da, is subtyping and variance. That thing I tried to get you to not think about for a while now. So yes, Rust does have subtyping. It arises from references, and it arises from the region relationship between lifetimes. So that's the crucial place where the language developers realized we need subtyping in the language. So here's an example of a place where subtyping is put into play. This pick function is going to take two references. One is a reference to some lifetime that has lifetime A, and another one is a reference to data that has static lifetime. And the crucial thing is it's going to return a reference that has lifetime A, points to something of lifetime A, but we can pass back Y. This is a place where we can pass back Y, this thing with static lifetime, as the return value. Or we could pass back X. Either one works. So this is a place where there's that compatibility, but at a deeper level in terms of what the compiler knows about. So the whole big idea here is that the static reference, that's something where we know that it's safe to pass that back and pretend that it's something that has a reference of lifetime A, because when you say that a reference has a certain lifetime, you're not making any statements about when it will die, you're just saying it lives at least this long. You're not making any guarantees that it actually expires at the end of that lifetime A. So, yeah, this is me repeating myself. The reference is able to be returned, and it's sound to do this, and there's this syntax in the language for describing this, you say that one lifetime outlives another by writing down lifetime, other lifetime, and we pronounce that outlives. So here we can say the static lifetime outlives the lifetime A. What about the other direction? What if we try to take a reference of lifetime A and pass it back as if it has static lifetime? And that's definitely rejected by the compiler. The compiler definitely rejects that because it's not sound. It would not be sound to take something of short lifetime or potentially short lifetime and act like it has a longer lifetime. That would be how you get dangling pointers. So, the crucial thing here is to see, for any type T and any lifetime A, clearly a reference of static lifetime T should be valid anywhere that a reference of the lifetime A of T is. So this is, again, something we can make that stripped-down example like I've been showing you before, where we pass in a static reference into a place that expects a non-static reference. Or we could write it down using Gensen-style rules, where we say if the static lifetime outlives the lifetime A, then the static reference should be a subtype of a reference with lifetime A. More generally, we can just not talk about static at all and just say, okay, if we have two lifetimes, B and A, and B outlives A, then there's a subtyping relationship between the two references, the one where the reference of lifetime B is a subtype of the reference of lifetime A. And furthermore, we've already established that a reference of static lifetime is a subtype of a reference of lifetime tick A. What if we go a little further? What if we have a reference to a reference? Should a reference of lifetime A that points to static data be a subtype of a reference of two references of lifetime A? I don't know, but intuitively, all you can do when you have an immutable reference is read the data from it. By that intuition, by the same logic that for functions, all you can do is call them and read the return types, so you're getting something out, same intuition applies here, and you can say, look, for immutable references, all I can do is pull things out of them. I can't store new things in principle. And thus, that's what leads to an argument that if y is a subtype of x, then in fact, yes, a reference to y is a subtype of a reference to x, which allows us to conclude that this question mark up here above is the reference to static data, or reference to a reference of static lifetime, a subtype of a reference to a reference? And the answer is yes, they are. And a way of saying this is that a reference to x is covariant with respect to x. Okay, that's immutable references, but what about mutable ones? Should a mutable reference to a static reference be a subtype of a mutable reference to a non-static reference? Well, we can take that same example from before, except now we don't have my cell. We take that same example and just use static data and make a reference to a reference, one of static lifetime and one with non-static lifetime. And in fact, the compiler rejects this. If the compiler allowed this, we could build the same picture that I showed earlier, the same stack frame layout, and the same effects in terms of the dangling pointer you'll get when you run this code. So it's important the compiler reject this. And therefore, it's important that when you have this kind of situation, then when you have a reference, a mutable reference to some data X, it's something where you can't have a subtype. You cannot use a subtype Y in that place. And to me, the intuition behind this is that once you allow mutation via a reference, once you have that level of indirection, allow mutation, the type has to remain fixed. You can't start trying to narrow the type at that point. And the easiest way for me to see this is by looking at other languages, like Java. So here's some code in Java. Quick show of hands, who thinks this code compiles? This is an array of numbers, and all I'm doing is I'm storing in a float, a new float that I create. And a hint here, float is a subtype number. Who thinks this compiles? Okay, interesting. It does compile. And also, Java arrays are covariant with respect to t. Array of t is covariant with respect to t, which means that you can actually create this function that creates an array of integers and passes it into the modify array function, which takes an array of numbers, and then stores a float into the array of numbers, which was secretly an array of integers. So now you have an array of integers that has a float hidden in it, which sounds bad. And it is bad. Java compiles this code, but gives you a runtime exception when you run it. The potentially infamous array store exception. So there's actually dynamic checks that happen in Java to ensure that you don't get unsoundness because instead they just fail. It's like their equivalent of panic, right? This is the Java answer. In Rust we say panic, and in Java they say runtime exception. This is an old historical artifact of Java. It predates their support for generics, where they have better ways to deal with these kinds of problems. So, going back to our earlier question then, that test I was using where I was talking about variance and looking at those examples and saying, well, does covariance apply here? And I said for all those examples I showed before, this example is not compiling, this example is not compiling. But now, in this situation, with this subtyping relationship where the reference to static data and a reference to non-static data, you can do the generalization where you plug in to the return type and pass along one function to another, and the compiler accepts it. So here's a place where we see covariance of a return type when we pass along these higher order functions. This compiles, you can follow the link to prove it. And in fact, Rust's functions are even contravariant with respect to their argument type in Rust. I mentioned contravariance before, and that's kind of interesting. A reason that this works for Rust and that Rust can support this is because we don't have method overloading. So the same conflict that comes up for languages like Java, where it conflicts with that other language feature, we don't have that language feature, so there's no conflict here. So I want to dive a little bit in and explain this variance thing a little bit more and how it works. So where does it come from? The answer is the compiler deduces the variance of your data structures. It does so by recursively traversing the structure of your types. So here I have an example of this outer inline data, and it has two fields. It has an instance of t on the field 1, and it has an inner field that just is an embedded inner inline object that itself has another instance of t. And the crucial thing is that the compiler, when it analyzes each of these structures, it traverses their structural definition and recurses into any other structures that are there to infer, these are both covariant with respect to t, which is interesting. And that's sound. It is sound to do this. But if you do something like add a mutable reference, then things change. So here I've now changed things so that the outer ref, that first field 1, stores a mutable reference to a t, while inner does not. Inner still has an immutable reference to t, or inner now has an immutable reference to t. And so now the compiler infers, there's potential mutation happening through this reference, which means that we are now invariant with respect to t. Outer ref is invariant with respect to t, while inner ref is covariant with respect to t. So there's some interesting things that happen that are very much underneath the hood in terms of you may not even realize the compiler is always doing this analysis for you to ensure soundness, to ensure that we don't get those dangling pointer examples that I showed earlier. And another detail here that the people who raised their hand for phantom data earlier might already know, if the compiler sees a phantom data is a zero-size type. It doesn't occupy any space in the type itself, in the structure itself. It's just there to pretend like you had an instance of this data in order to get the variance relationships that you want. That's one reason for it, that it's there. It's for variance relationship, and it's also for stuff with destructors, which you can come talk to me about afterwards if you care. There's some really grotty details about destructors and forcing them to run at the right times and not have dangling pointers in your destructors. So, going back to our cell and unsafe cell example, the unsafe cell is known to the compiler. It's a language item the compiler knows about, and so the compiler treats it specially and says, this is invariant with respect to t. And because of that, that property bubbles out to cell when it recursively descends into cell. Versus my cell, where the structural definition alone, the compiler inferred that it was covariant with respect to t, and the method that I showed, the set method, breaks the rules associated with that. So that was the fundamental problem, is that the set method was not sound. It was an incorrect use of unsafe because the structure definition has implications for the relationship between t and my cell that are not preserved by the set method. Because the structure should be imposing an invariant relationship. My cell should be invariant with respect to t the same way that the cell data type is. So one solution to this would be to use phantom data again. You can actually use phantom data and input a function from t to t. Remember earlier where I was talking about what if you have a y arrow y and an x arrow x, and you want to, what is the relationship that implies that y arrow y is a subtype of x arrow x? And the answer is y has to equal x. They have to be invariant with it. They have to be not subtypes of each other. They actually have to be equal. So a function from t to t is a way of saying this thing has to be invariant with respect to t. So that's one way to accomplish this, is to use a phantom data. But forget I said that. If you get nothing else out of this talk, I really need to be careful about this. If you remember nothing else from this talk, it is don't do the my cell example the way I showed you. Use unsafe cell, because it's going to get it right. It's really important to think about that ahead of time. If you're going to, at least if you're going to use any unsafe code. Once you start using unsafe code, you need to really think hard about, should I be using unsafe cell instead of what other magic I might be using. Okay, so now I want to go back to those examples I showed at the beginning, where I talked about all these examples that seem like they might be subtyping. And I'm calling those duck subtyping, in the sense that there's duck typing, where if it walks like a duck and it quacks like a duck, it must be a duck. Here my argument is in fact the opposite, where I'm saying, yeah, those walked and quacked like subtyping relationship, but in fact they're not, because they missed that crucial variance thing with how functions are handled. So what are they if they're not subtyping? What's going on? So yeah, here's where I show you the secret behind the magic and what's going on behind the scenes. So what is actually happening there? And the answer is a whole bunch of stuff. There's a whole collection of different technologies that are interacting to get those effects that I showed you earlier. So there's coercions that are happening. In particular, when you have a method call x.m, or a field dereference, the compiler actually will magically insert either a borrow of x or as many dereferences of x that it needs to in order to find the member that you asked for. So this is a reason that Rust, who here has programmed in C++, or C for that matter? Okay, good. So there's this distinction in C and C++ between the dot operator and the arrow operator, right? Sometimes you need to do x.f, and other times you need to do y arrow f. And that always bugged the heck out of me before I understood what it was, the difference in what they were expressing. Rust doesn't need the two syntaxes, because it's basically magically using dot all the time and figuring out, where you needed to have an arrow, I'll just let you use dot and I'll put in the dereference. And in fact, I'll put in multiple dereferences as many times as I need to. And there's a Stack Overflow question that documents how this works pretty well that I linked to. So that phenomenon of this automatic borrowing or dereferencing is what explains the grid I showed earlier with that character array. The fact that we were able to pass in a value into something that wants a reference or wants a mutable reference, that's explained by the fact that we'll automatically borrow. And likewise, the fact that we're able to pass in a reference into something that wants a value, that's explained by the fact that we'll automatically dereference. One note here, this special coercion, this particular coercion only applies to things that are the receiver of a method call or a field access, the X dot something. The dot is special there, and that if you have an argument that occurs somewhere else in the argument list, they don't get this particular treatment. And the main argument for why that's the case and why we don't attempt to do this automatic borrowing dereferencing is that basically there's cases where you don't want to infer it, you don't want to implicitly be borrowing things, because one, the error message you get when you can't find an appropriate borrow dereference become pretty bad. So it's hard to make good compiler error messages. And also, a lot of people prefer to have the borrows be explicit in order to just see in the code, oh, I'm actually taking a reference here. For some reason, I don't quite have a good argument for this, but for some reason, that disconnect where people want to see the explicit borrows on arguments, for some reason it doesn't quite apply to the receivers. And I don't 100% understand the psychology here. All I know is I agree with it, like my own self. So maybe in 50 years, someone will do some cognitive science experiments and figure this out. Okay, another kind of coercion is deref coercion. If I have a reference to a y, and I can dereference y to get an x out, the compiler actually will automatically coerce a reference to y into a reference to x by automatically inserting dereference operations. And that is what explains the ability to go from vec to a slice. And then there's automatic reborrows as well. If you pass a mutable reference into an expression context that's also expecting a reference, the compiler actually will automatically insert a reborrow and a dereference. And it does this in a lot of places. The compiler actually inserts these in lots of places just based on the fact that it says, oh, there's an expected reference here and I'm passing in a reference. Let's go ahead and reborrow it here. The reason that it does this is that lots of times when you pass in a reference to a t, you don't really want to move away that reference to the argument. You'd rather have it be a new reference that has a shorter lifetime so that you can go ahead and modify the reference afterwards. There's a great blog post called Stuff the Identity Function Does, where literally Bless just writes down the function that takes a value and takes a t and returns a t. And you would think that that's a silly function. What would you use this for? But he points out that there's an issue here where it causes an interesting effect that interacts with this phenomenon. So I recommend reading that post if you have not already. Then we have protocols. You have things like that phase 1, phase 2, where I was turning an AST into mir and then a mir into output. And the question was, well, we have two different kinds of errors, and yet we somehow got end-to-end error. So that was that code again, where we have two different kinds of errors, phase 1, phase 2, and we compose the two functions, and we somehow got end-to-end error out. So are phase 1 error and phase 2 error subtypes of end-to-end error? You probably already know the answer. The answer is no. The answer in this case is the magic is all hidden behind the try macro. In particular, the try macro actually expands into this little match expression, and part of that match expression calls this standard convert from function. So, and there's this question mark form that is in the nightly compiler. It's the same. It behaves the same as try. I showed you try because I can easily show you the macro expansion of try, but question mark does the same thing in this case. And the important thing is that there's a conversion being inserted so that the error gets converted from one error into another automatically based on the context. So in this case, we have that particular arm where we got an error and we have the conversion there. That combined with these things I didn't show you. I didn't show you the from implementation for the two kinds of errors, for phase 1 error and phase 2 error. This is the magic sauce that's allowing us to just compose those two functions without any extra effort. Finally, there's some gotchas I want to note here. I went over these things about coercions and automatic reborrows. In order for them to apply, the compiler actually has to know what the expected type is. It actually has to know what the thing is being coerced to. If the compiler doesn't have that information, then it can't do the coercion. So the example I have here is that there's a process function that wants a slice and gets a reference to a vector. And that works. It compiles. But process 2, it's generalized. It says I take any input at all where the input trait is implemented for a slice, for an unsized array of I32, and the compiler rejects this bottom case, even though these two things look like they should both work in principle. The reason this doesn't work, well, the first case is obvious. As I said before, a reference to a vector can be coerced into a reference to a slice. But the second case, The compiler has to decide what is the type I, and it infers the type I must be vec of I32. It does this type inference unification thing and determines it commits early on, says I must be a vec of I32, and once it decides that, then it goes and says, well, let me go find an implementation of the input trait, which of course doesn't exist here. And that's why that fails. You have to actually do the coercion yourself manually. You have to add in something like an as slice call in order to get that effect. Okay, so those are all my examples and whatnot. I'll take questions, I think, in a moment. Pop quiz. So what's the relationship between these references here? You know, who knows? Is the static reference a subtype of a reference of lifetime A? What about a reference to a reference when the thing you're pointing to is static? And what about a mutable reference to a static? Well, one answer is that how often do you actually ask this question? Maybe you shouldn't worry about it too much. Subtyping in Rust doesn't have to be in the forefront of your mind, in fact. And I have other arguments for why subtyping can't possibly be that important in Rust, but I won't talk about it here. But in case you're curious what the answer is, it's yes, yes, no. Okay, so, and what about this variance thing? And the answer is that getting covariance and invariance right does matter. It matters a lot for soundness properties. I already showed you the example of a dangling pointer. But you don't need to think about it unless you're writing unsafe code. So because if you don't have any unsafe code, then it's the compiler's job to get this right. I already said before, the compiler is inferring the variance of the various types. So you don't need to think about invariance or think about variance if you're not doing unsafe. And in fact, it turns out, I'd argue you don't need to think about variance even if you are doing unsafe, as long as it's not unsafe with generics. It's when you start mixing unsafes with generics is when you get to start having those reference types getting thrown in there secretly that you didn't anticipate, that you need to then worry about in terms of the dangling pointers that arise. But if you're doing unsafe code where the types involved aren't generic, they're always just arrays of integers, for example, and there's no references, then you probably can get it right without thinking too hard about this. Okay, there's more information about all these topics, namely in the RFCs, like the deref coercion RFC. The book, I don't know, Steve, if the book covers this topic in that much detail, but you can look there and find out. And the Rustonomicon does delve deeply into a number of these things, but I did notice it basically has a to-do for the thing about how method dispatch goes and the automatic borrows and reborrows and dereferences. So not only look at them, but contribute back to them. Go ahead and see if you can find some way to express these properties and give back to the community. And finally, this sort of the theme of this talk was to ask questions the whole time and to wonder about subtyping and explore it. So explore through code, but also make sure you do the experiments properly. Don't just assume that you understand what's going on. Try small variations. Like I said with the second Clarke law, you need to push the boundaries in order to discover what the impossible things are. Do that. And finally, the magic in Rust, it's as real as you want it to be. If you want there to be no magic, then go ahead and learn about the compiler, learn about how everything's implemented. But it's okay to believe in magic. So you don't have to learn how the compiler works in all cases. You can trust the magic underneath the hood. That's all.
Thank you very much. Unfortunately, we don't have enough time for questions right now. We're running a bit late. So we're going to take a 10-minute break right now. I'm sure Felix is available for questions during the break.